Hello everybody, myself Prasanta Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In our last class of power electronics and drives, so we have discussed about voltage commutated choppers. So since we have started the class with different methods of commutations of choppers, and there we have discussed that force commutation and say load commutations. Force commutations was actually voltage commutated choppers and line commutated or current commutated choppers, and then we have discussed about the voltage commutated or impulse commutated chopper circuits, its design considerations, that is commutating design of commutating capacitors and commutating inductor. Today we'll discuss current or resonant pulse commutated chopper. So this is the circuit diagram of resonant or current commutated chopper circuit. We are coming in details of this circuit diagram. So basically this basic power circuit for this current commutated chopper is shown in this figure, and here this thyristor T1 is the main thyristor, and the commutating circuit consists of this thyristor 2 T2 actually, and a capacitor C and inductor L and diodes D1 and D2. So this is main thyristors, and this is commutating circuits consisting of this T2 capacitor L, C inductor L, and diodes D1 and D2. And DF basically this is the freewheeling diode, and R is the charging resistors here. So it is the charging resistors, and the main thyristor T1 is commutated by a current pulse generated in the commutation circuitry. And the important features of this type of chopper is that the reverse voltage across the device is applied through a diode connected in anti-parallel to the SCR. So this is here. So actually, since this is limited to about 1 volt, the turn-off time of SCR increases in comparison with the voltage commutation circuit. So basically, this is actually the circuit. So this is the commutation circuits, and this is the main circuit. So this is the load, and this is freewheeling diode. This is charging resistors, and this is the thyristor. Main thyristor is T1, which we want to commutate, and this is the commutating circuitry. So this is this thyristor T2, this diode D1, D2 charging capacitors and inductors are forming this commutating circuit. So now as in voltage commutated chopper, here also energy for current commutation comes from the energy stored in a capacitor here. So to start the circuit, the capacitor is charged to a voltage EDC, like a voltage commutated choppers also. Through the path, this is actually EDC positive, C, R, and EDC minus. So this is actually EDC positive, C, R, and EDC minus. So this is the charging circuit of this capacitors, commutating capacitors. Okay, so this is the path. Okay, now the main thyristor T1 is triggered at say time t equal to T0, so that the load voltage is 0 EDC and the load current I0 equal to IO max up to t equal to T1 is impressed. So see, this is actually says IO equal to IO, so this is the path. Okay, now this is actually shown here in this figure. See, see t equal to T1 up to T1. So this is actually this current. Okay, so through that is IT1 up to T1, and the voltage is EDC. Okay, so this is voltage. This is the charging voltage, and this is the ET1, and this is the output voltage EDC. Okay, so this is the voltage and current waveforms of the current commutated chopper. Now this actually after this, and What is mode of operations will be discussed. For convenience, the commutations process is divided into certain modes and it is explained. First, mode 1 operations at time t equal to t1, this auxiliary thyristor t2 is triggered to commutate at the main thyristor t1. So actually this is t1 is commutating circuit, t2 is commuted as being at t1 auxiliary thyristor T2 is triggered to commutate the main thyristor T1, that is here when it is in conduction. So T2 will be at T1 it is triggered to commutate the main thyristor T1. So basically this is used to turn off this thyristor T1. So this is the part of the commutating circuit. This is the main component of the commutating circuit, this T2. So, and when this thyristor, auxiliary thyristor T2 is turned on, an oscillatory current, that is charging current IC equal to EDC by omega RL sine omega T is set up in the circuit consisting C, T2 and L. So since it is a LC circuit, so it is a oscillatory circuit. So actually it is when this auxiliary thyristor T2 is turned on, an oscillatory current is set up, that is equal to the EDC by omega RL sine omega T is set up in the circuitry consisting of C, T2 and L. So that is shown here. This is this circuit. Okay, when it is on, so basically this will be like this. Okay, so since it is fully charged. Okay, so this is the oscillatory circuits, and the oscillatory current is given here. And at T2 the capacitor current IC reverses, therefore SCR T2 gets turned off due to natural compression, and T2 and at T2 VC capacitor voltage is equal minus EDC, and in this mode the main thyristor T1 remains unaffected, and hence load voltage and load current remains EDC and IOM respectively. So that is shown here. So you see, this is actually load current, and this is actually the load voltage. So this is unaffected at T equal to T1. Okay, so this is a T2 turn on, and at T2 time T2, small T2, so this thyristor T2 is turned off. Okay, and see, this is actually this oscillatory current. This is the oscillatory current. Okay, this is basically this is the capacitor current. Okay, this is the current to the main thyristor, and this is the load current. So this is the maximum value of the load current, output current, and this is actually the gate signal which is given to the gate of the thyristor 1 to turn it on, and this is the gate signal given to thyristor 2 or auxiliary thyristor to make it on. So this is at T1. Okay, so this is actually mode 1. So this is actually mode 1 from T1 to T2. So this is mode 1. Okay, and mode 2 will start from T equal to T2 to this T3. So this is mode 2. Okay, then let us come to the discussions about the mode 2. What is happening with mode 2? So in mode 2, since T2 is turned off at the time small T2, oscillatory current IC flows through CL and D2 and T1. Okay, so this is the oscillatory current CL, D2 and T1. So this is off. So this is the oscillatory current flowing D2. It's actually like this. Oscillatory current will be like this. So flowing. How it is flowing? So this is flowing in this way. Basically, oscillatory current is flowing CL, D2 and T1. CL, D2 and T1. See, this is like this. C, L, D2 and T1. Okay, oscillatory current is flowing through this, and not through D1. So So after T2, current IC would flow through T1 and not through D1, because D1 is reverse biased by a small voltage level conducting thyristor T1. Hence, after T2, IC, this capacitor current would flow through T1 and not through D1. And as current IC flows in the opposite direction in T1, it decreases the current of the thyristor 1, IT1. And at T3, this IC equal to IT1, and so the net current through T1 is 0 and it turns off. And as the oscillatory current through T1 turns it off, so it is called as a current commutated chopper. So because of this oscillatory current which is flowing to turn the T1 and makes it turn off, so it is called current commutated chopper. And during this mode, load voltage remains EDC through T1. So that is shown here. So from T2 to T3. So this is actually this from T2 to T3. This is actually this current. Okay. Here, this is the time period. This is T2 and this is T3. So make this current IT at TC, this is 0. Okay, and this is turned off. Clear? So actually, this is the operations of at mode 2 operations. So basically, at T3, IC equal to IT1, and so the net current through T1 is 0 and it turns off. And as the oscillatory current through T1 turns it off, so it is called as current commutated choppers. And during this mode, load voltage remains EDC through T1. And at mode 3 operations, since T1 is turned off at T3 and IC becomes more than the load current or output current I0. So after T3, IC supplies load current I0 and diode D1 begins to conduct the current, the difference of this current IC minus I0, and the drop in D1 due to this current keeps the thyristor T1 reverse biased for the time. So this is a TQ, that is equal to T4 minus T3. So that is also shown. And at mode 4 operations, at T4, this IC equal to I0 and current through D1 diode 1. So ID1 is 0 and therefore diode D1 is reverse biased. And after T4, a constant current equal to I0 flows through the path EDC, C, L and DL and to load. So EDC, C, L, DL and load. That can be shown here. EDC, C, L, DL and the load. So actually, so that is actually shown here. Actually, at mode G, C, L and DL and load, and therefore capacitor C is charged linearly to source voltage EDC at T5. And therefore during the period T4 to T5, IC equal to I0, and as D1 is turned off at T4 and VC equal to ET1, now the load voltage E0 equal to EDC minus VC at T4, and at T5 VC equal to EDC, hence at T5 load voltage becomes E0 equal to EDC minus EDC equal to 0. And during this interval T4 to T5 VC increases linearly, and therefore load voltage E0 decreases to 0 linearly and during this period. And at mode 5 operations, as that is shown, at T6 capacitor C is actually overcharged to a voltage somewhat greater than source voltage EDC, and therefore at T5 the freewheeling diode DF becomes forward biased and starts to conduct the load current IO, that is output current. So as IC is not 0 at T5, the capacitor C is still connected to the load through EDC, C, L and D2, and then as a result, C is overcharged by the transfer of energy from L to C, and therefore at T6 IC equals 0 and VC becomes more than EDC. So that everything is discussed in this waveform of the current commutated chopper. And during this interval T5 to T6, I0 equal to IC plus IF, that is, and therefore as IC decays, IF builds up at T6, IF equal to I0 and IC equal to 0. So commutations process is completed at T6 and the commutation interval is T6 to T1. Okay. So from T6 onwards, load current freewheels through DF and decays, and as IC is 0 and D2 is open circuited, capacitor voltage VC decays through R for the freewheeling period of the chopper. And at T equal to T, that is the chopping period, the main thyristor T1 is triggered again, and the cycle repeats. And this chopper is developed by Hitachi Electric Company, Japan, and it's widely used in trucks and cars. And this is actually the case of say current commutated choppers, and this is discussed in details. Its circuitry, as I told you, this is the circuitry of current commutated chopper. This is the main circuit, main thyristor which we need to commutate, and this is the commutating circuit, so consisting of this auxiliary thyristors, say commutating capacitors, commutating inductors, and this diodes D2, D1, etc. And there are 5 modes of operations we have discussed one after another. And initially this capacitor is charged like voltage capacitors and voltage commutated choppers, and then at say T2 at T equal to say actually at a time T equal to T1, so this is say S2 is triggered to commutate the main thyristors, and then one after another. So it is mode 2, mode 3 operation, mode 4 and mode 5 operations was say continues, and this is actually depicted in this voltage and current waveforms of the current commutated chopper. So basically at T0, so this thyristor 1 main thyristor is on at T equal to T1, so auxiliary thyristor is on, and it is at T equal to T2, this auxiliary thyristor is off, and from this is actually this T up to T1 to T2, this is the mode 1 operations, and from T2 to T3, this is the mode 3 operations, and at T3 this auxiliary thyristor is off, and from T2 to T3 mode 3 operations is continues, where the main thyristors T1 is off, and from say T3 to T4 the mode 3 operations is being conducted, and at T4, so basically this diode 1 is off, and this is actually at T5, so this is freewheeling diode is on, and at T6 it is being completed, and this is the chopping period after at T. So this is actually voltage and current waveforms of the current commutated choppers. And if we discuss about the advantages of this current commutated choppers, we get the following advantages here. So that is the capacitor always remain charged with the correct polarity, first one, and secondly, commutation is reliable as long as load current is less than the peak commutation current, that is ICP, and the auxiliary thyristor T2 is naturally commutated as its current passes to 0 value. So the main design considerations is you have to select in a proper manner the commutating components values, this inductor L and the C, so that it can satisfy for reliable commutations. First conditions is reliable commutations of the main SCR T1. So first condition is the peak commutating current ICP must be greater than the maximum possible load current and IOM. And this condition is very essential for reliable commutations of the main SCR, that is T1. And the oscillating current is given from this, say, actually we have seen this equation, this is IC equal to EDC root of C by L sine omega T. So this is equal to ICP, so it is ICP sine omega t. And for from condition A, that is the peak commutating current ICP must be greater than the maximum possible load current IOM. So for that, this value ICP is this is the ICP is to be greater than IOM, and so EDC root of C by L, it is some component, say factor x into IOM. So IOM definitely, if IUCP is greater than IOM, so x must be greater than 1. So therefore x is what is the value of x? X equal to ICP by IOM. So and second condition is the circuit turn of time. So TQ must be greater than the thyristor T1 turn of time. So T off. So therefore circuit turn of time TQ should be T off, this T off plus delta T. So basically from actually say waveform, so we find that TQ equal to T4 minus T3, and if we clearly say observe the waveforms, so we will find the current waveforms that we can write TQ equal to T4 minus T3, or omega R TQ equal to pi minus 2 theta 1. And so also ICP sine theta 1 equal to IOM, or theta 1 equal to sine inverse IOM by ICP, so that is equal to sine inverse 1 by x. So this is actually say 1 by x. So circuit turn up time for main shear T1 from this equation is TQ equal to 1 by omega pi minus 2 theta n to theta 1. So substituting this value of theta 1 from equation this equation, so we get actually the turn of time, circuit turn of time TQ equal to 1 by omega pi minus 2 theta inverse say IOM by ICP. And from these equations it is clear that as load current IOM is increases, circuit turn of time for main shear T1 decreases. So and therefore there's a certain value of ratio IOM by ICP must be maintained for ensuring unnecessary turn up of the circuit turn up TQ. And if we substitute this value of omega r equal to 1 by root LC in these equations, we get TQ equal to root over LC pi minus 2 theta inverse 1 by x. So root C equal to TQ by root L into say pi minus 2 sine inverse 1 by x. So substituting this value in the first equations of say ICP, this actually this equation, so ICP, so we'll get this we get so EDC by L TQ by pi minus 2 sine inverse 1 by x equal to x into IOM, or L equal to this. After simplifications we'll get this value of the L, and if we put this value of L in this equations, so we'll get the value of the C, and C will be x IOM TQ by TQ into pi minus 2 sine inverse of 1 by x. So this is actually the circuit design considerations for getting the commutating value of the commutating inductors and commutating capacitors. And secondly, peak capacitor voltage can be found from the waveforms current waveforms of the current commutated choppers. It is clear that the maximum capacitor voltage is reached at T6, and therefore voltage at T6 equal to VCP, that is voltage at T5 plus voltage rise due to energy transfer from A to C during T5 to T6. So at instant T5, energy stored is in L is half L IOM square. So it is a common equation for the energy stored in inductors, and at T6, this energy is transferred to the commutating capacitor C, and thus the voltage rise of the capacitor C due to this transfer to energy is half C VC square, that is half L IOM square. So or VC equal to IOM root of L by C. And now if we substitute this value of this into the first equations of VCP, we'll get VCP equal to EDC plus IOM root over L by C. So this Peak voltage and current value of the capacitor are also the peak ratings of the both the main and auxiliary thyristors. And the charging resistor R is selected such that the chopping period T is much greater than say 3 times this RC. So this is actually say time constant. So basically this all about the current commutated chopper, and hope you have so understand it. So what we have done here, we have in this post commutation process, so this current commutation process, we have say try to establish that in what way it is beneficial or it is better than voltage commutated chopper, and what are the advantages of these choppers, what are the different modes of operations of this current commutated choppers, from starting from the say charging the commutating capacitor C, and then from the different operations from mode 1 to mode 5, and we have since, and then the corresponding say waveforms, voltage and current waveforms of different components. I mean, say commutating thyristors, auxiliary thyristors, it's gate signals, voltage, etc. We have say drawn here. So that is, and we have discussed here. And last of all, we have say discuss about the different say advantages of this current commutated choppers. What is its reliability, and to make this reliability established, we have also considered the design considerations of the commutating say components, that is inductors and the capacitors, and also we have tried to find out the peak voltage to the capacitors. And so during this process we have taken into considerations the two conditions for design condition, that is peak commutating current must be greater than the maximum possible load current IOM, and secondly current circuit turn-off time T2 must be greater than the thyristor T1 turn-off time T-off. So with this we have they tried to establish this operation, design consideration, advantages of this current commutated choppers. So from the actually this outcome of this discussions is that, so if you are when you will work with this, so you have say capable to deal with this current commutated chopper circuits, and you can better understand its operational procedures, its how it is being used in say commutation process of the choppers, and why it is better, and how it can be designed, what are the design considerations, what should be the conditions you have to fulfill to consider the or select the value of this commutating capacitors and say commutating inductors, and hope you have say able to understand it, and you can say if you go through your say go through this lecture carefully, and if you study your textbook, so I'm sure that you will be able to understand this current commutated chopper in a better way. And last of all, like my all say lecture, I am telling you say instead of all this process, you are not able to understand the subject properly. So I am open, I am available for you to make you understand the say subject, and my details of say communications address are given into my say very first lectures. That is my email ID, my WhatsApp number, my mobile number, and my everything is given. So hopefully you will be able to understand the subject. So and you have enjoyed it. So I am once again thank you all for giving your say patient learning, patient hearing of this subject. So thank you all.